So I wanted to start today by just kind of rehashing the last thing that we looked at on Monday. Last thing that we looked at on Monday was Dalton's law of partial pressures, and we kind of hurried our way through it there at the end because we were running out of time. So I just wanted to take a second and re-highlight the features here. So when we measure the pressure of a gas, we are measuring the pressure of all of the components of that gas all at once. So if it's a pure sample of gas, then it's easy. If I've got an oxygen tank, the pressure I measure of the oxygen is what it is. I don't have to worry about kind of cycling back and looking at, okay, well, how much of it is oxygen, how much of it is nitrogen, how much of it is air, and other things. I don't have to do that. The pressure is what the pressure inside is. So pretty easy to follow. But if I'm dealing with a mixture of gases is going to have different components. And each one of those components is going to have its own pressure. We call those individual pressures partial pressures. And so what Dalton's law says is that if I'm looking at a sample of gases that are a mixture of gases, the overall pressure that I measure is equal to the individual pressures that each one of those gases exhibits, all added together. And that's all well and good, but it does create one particular problem for us. What if, in the instance of a chemical reaction, I'm only interested in one of the components of that mixture of the gases? How do I go about figuring out what its individual pressure is? Now, you saw a little bit of this in the lab. When you did the molar volume of the gas lab, you collected oxygen gas in that, but you collected it over water. And so the mixture of gases that was over the water there was not only the oxygen that was created by the chemical reaction, but also water vapor that had naturally been occurring from the water evaporating. And so when we measured the pressure of that mixture, it wasn't just oxygen, it was oxygen and water vapor. Now we were able to account for that because water has a measurable vapor pressure, and we could look up what that pressure was and subtract it out. But what if we didn't have that kind of information available to us? Well, what we would have to do instead is we'd have to rely upon this relationship based on Dalton's law. And the relationship is that the individual pressure of a gas is equal to the total pressure of the gas multiplied by this value. This value here, XA, is something known as the mole fraction. Now, what is mole fraction? Mole fraction is basically the proportional amount of gas relative to the other gases in total. So to find mole fraction of a component of the gas, I need to look at the number of moles of that gas specifically versus the total number of moles in the sample. So if I'm measuring out the gases proportionally, I can do that relatively easily. I can say, okay, well, I've got 32 grams of oxygen, and I've got 16 grams of methane, and I've got this of that, and I can calculate all the moles of those things. And I can figure out, okay, well, I've got 5 moles in total, and 1 mole of that is oxygen. 1 over 5 is 20% or 0.2. That's my mole fraction. If I know the pressures, I can figure out the mole fraction based on the ratio of pressures as well. And what this allows us to do, this relationship of mole fraction, ultimately allows us to answer questions like this. In this question, we are told the atmosphere is made up of several gases, each of those gases listed by their percent composition. If atmospheric pressure is 0.891 atmospheres, what is the partial pressure of oxygen gas in the atmosphere? Well, what this table tells us is what is the relative percentage of each component of air. And so we can see from this table, nitrogen is a little bit more than 78% of air. Oxygen's a little bit less than 21%, and all of the other gases make up the remaining little bit more than 1%. Now, the question here is asking specifically about the oxygen. So, if I am interested in the partial pressure of oxygen, I need the mole fraction of oxygen and the total pressure. The total pressure we were given 0.891 atmospheres. The partial pressure, or excuse me, the mole fraction, comes from this value right here. We're told that the fractional percent of oxygen is 20.948%. Now, 20.948% is equal to, from a fractional standpoint, 0.20948. And that is the value we would put in for the mole fraction. Basically, if we have percentages, we just take off the percentage aspect, we divide by 100. If we already have it in decimal form, then we just plug it in as its decimal form. So 0.20948 is the value there. And so that means that the partial pressure of oxygen, 0.20948 times 0.891 to three significant figures would be 0.187 atmospheres. So this is one thing that we can do using Dalton's law of partial pressures. We can actually figure out what is the individual pressure of gas, and then from there, use it. You know, we talked a little bit on Monday about the ideal gas law. Well, if I'm looking at the ideal gas law from a standpoint of a chemical reaction, I only need to know the parameters, the pressure, volume, and temperature of the gas that is actually reacting or is being produced in the reaction. If I'm measuring it out of the air, I can't just simply take the atmospheric pressure. I have to know the partial pressure. So this is where that kind of an application would be used. All right, any questions with this example here? All right, so there are two other concepts. Well, there are two small concepts and then one big one. The first small concept is related to something we saw the first day we looked at gases. So if you remember back to last Monday, we talked about the concept of root mean square velocity. That is the relationship between a gas's speed at which it moves and its molar mass. And so we were able to make some very broad kind of generic statements related to those two ideas. Heavy gases move slow, light gases move quickly. Well, Graham's law here takes that idea and allows us to compare gases directly. Now, just as a point of clarification, Graham's law refers specifically to something called effusion, Effusion. Effusion is the movement of gas through a small hole. So let's imagine that you blow up a balloon and then you take a pin and you just gently prick a small hole into that balloon. Not so that it pops, but so that gas slowly bleeds out of the balloon and it starts to deflate. That process of the gas bleeding out of the balloon, that is effusion. It is different from diffusion. Diffusion, you've probably heard before, maybe in biology class, about the idea of when things mix. We talk about osmosis, the movement of water from an area of high concentration to low concentration. We talk about cellular diffusion, where salt or sugar or other things that are not water move from an area of high concentration to low concentration. Diffusion is a general process that happens when we get things moving from areas of high concentration to low concentration. And for gases, that usually means that we're mixing things up. So what we're interested in out of Graham's law here is this equation. This equation gives us the relationship between how quickly a gas effuses, how quickly it moves, and its molar mass. And we can see that just like we talked about last Monday, the rate ratio is inverted. Faster gases are lighter, heavier gases are slower. But now we have a much more quantitative way of relating them to each other. Not only are they faster or slower, they're faster or slower dependent upon the square root of the ratio of the masses themselves. So if I have something that is double in size, it's not going to move double the speed slower. So if I double the molecular weight, it isn't going to cause the gas to move half as quickly. It's going to be the square root of 1/2. That's where that square root is going to come. And what that'll allow us to do is to answer questions like this. So we have ammonia gas. Ammonia gas reacts with an unknown acid. So I've got 2 cotton balls that are soaked in ammonia and acid. Those liquids volatilize, turn into gases, and the gases start to effuse through this glass tube until they come into contact with each other. And when they come into contact with each other, they form a chemical reaction that gives us a solid product. Our question is this: if the ammonia traveled 2.74 times faster than the acid, what acid are we talking about? Now, how do we go about solving this out? Well, this is where we would use Graham's law. So Graham's law, R1 over R2 is equal to the square root of M2 over M1. So inverse relationship, but a square root relationship as well. Now, here's where we can kind of help ourselves out a little bit. If we define the ammonia as our R1 and our M1, what this is saying, the ammonia traveling 2.74 times faster, that means that the ratio of rates, R1 versus R2, is equal to 2.74. R1, the rate of ammonia, is 2.74 times faster than R2. So I can put in 2.74 as my value of R1 over R2 because that's what the relationship tells us it is. Now I just need to figure out the mass piece. Don't know what M2 is. That's what I'm trying to figure out. M1 is going to be the molar mass of ammonia. Ammonia, 14.01 for the nitrogen, and 1.01 for each hydrogen times 3, because there are 3 of them, 17.04 grams per mole. So I'm working in algebra here. How do I get rid of the square root term so that I can solve what's underneath? Yeah, I got to square both sides. So I got to square the right-hand side and I got to square the left-hand side. 2.74 squared is 7.51. Squaring the square root gets rid of it. I've got M2 over 17.04 grams per mole. And now to get rid of the 17.04 grams per mole in the denominator, I've got to multiply each side by 17.04 grams per mole. So I've got M2, 17.04 times 7.51. To 3 significant figures is 128 grams per mole. Now I look at my options. Hydrogen is going to be one of those grams, which means I need 127 grams for the other element. I look at my options. Iodine, 126.9. That's pretty close, certainly close enough. So we're looking at hydrogen iodide, HI, here as my acid. So Graham's law has a lot of kind of interesting applications for us. First of all, we can use it to do things like this, identify unknown gases based upon relative rates of motion. We can also flip it around. If I know what the two gases are, I can predict how much faster one will travel compared to the other. All I need to do is just put in the masses, take the square root of that ratio, and it's going to tell me how much faster or slower that first one is compared to the second. Right? Any questions related to Graham's law? Okay, the other small concept that we want to look at before we get into gas phase stoichiometry takes us back to another thing that we talked about last Monday, the kinetic molecular theory of gases. We talked about the idea that gases are governed by these ideas. And 2 of the ideas in play were that gases have no volume because they are so small compared to the size of their container. And gases do not experience intermolecular forces because gases are too far apart to do so, and they're moving too quickly. Well, for almost every scenario, this holds true. And certainly if we are at normal kinds of conditions, not even necessarily STP, but just normal atmospheric conditions, normal temperature conditions, this works out really well. We can use the ideal gas law, we can use the combined gas law, everything kind of works out really nicely. But there are two sets of conditions where it doesn't work out so nicely. If we are at high pressure means one of two things. Either we have packed our container so full of gas that the gas molecules are starting to kind of get in each other's way, or we have shrunk down the volume so considerably that those gas molecules are kind of on top of each other. In either scenario, we're not seeing that great distance between the gas molecules. And so that first assumption that we made isn't true anymore. The other scenario that can be kind of potentially dangerous for us is what if we're at low temperature? Well, if we're at low temperature, we know that that means that the energy of the molecules themselves, how quickly they move, isn't as quick as it used to be. And so one of the ideas that was separating intermolecular forces from existing is the fact that the molecules were moving so fast, they don't have time to interact with each other. But what if we slow that process down? Well, if we slow the process down and they start moving a lot slower, they are going to have the ability to interact with each other and draw themselves to each other. Intermolecular forces are now something we have to consider at low temperatures. And if we have a combination of both of those, a high pressure, low temperature kind of gas, then the assumptions and the failures of those assumptions multiply. So how do we account for these deviations from kinetic molecular theory? And the answer to that question is the answer that we always have when we encounter trouble. If your theory is no longer good, fix the theory. If that still doesn't work, then maybe you need to start looking for a new theory. But if we fix the theory, what we get is something called the van der Waals equation. The van der Waals equation allows us to account for these differences at these particular scenarios. If you look at the heart of the van der Waals equation, you see the ideal gas law. PV is equal to nRT. The only difference between the van der Waals equation and other equation, the ideal gas law, is that there are corrections added to the pressure and volume. Gas molecules no longer negligible in size. Let's correct for that. Let's subtract out a term here from the volume to account for the size of those molecules. Molecules exhibiting intermolecular forces when they're not supposed to, let's correct for that. Let's add something to the pressure term here so that we can account for the fact that those molecules are no longer just unattracted to each other. So N in both of those cases is the number of gas molecules, number of moles of gas. The lowercase v, velocity. So that's your temperature relationship. A and B, those are constant values. They are related specifically to a substance. So oxygen has its own set of A and B values. Carbon dioxide has its own set of A and B values. Pretty much any gaseous substance has their own A and B values. Those have been experimentally determined. You would find them in reference tables. Now, here's the good news for you. I'm not going to ask you to use the van der Waals equation. I'm not going to ask you to calculate anything using the van der Waals equation. Why I'm presenting it is just I want you to know that the ideal gas law does not work in every situation. And so rather than discard the entirety of the kinetic molecular theory, the entirety of the ideal gas law, we make adjustments accordingly based upon the information that we have. One last big concept, gas phase stoichiometry. Now, ever since module 4, we have been looking at stoichiometry in some way, shape, or form. And ultimately, every single time we've done stoichiometry, it has been the relationship between something that we can measure and moles. Now, way back in module 4, we were using primarily grams. Grams were the thing that we could measure on a balance and then turn them into moles using molar mass and balanced chemical equations to convert one substance to another. In module 5, we introduced the concept of solutions. And what did we do in that case? Well, we know that we can measure the volume of a solution, and we could tie volume to moles using molarity. Pretty much the same idea here. Gas phase stoichiometry just takes our idea of moles and relates it to something that we can measure. Now, for gases, what can we measure? Pressure, volume, temperature. Pressure, volume, temperature, moles. That sounds like the ideal gas law to me. And so the ideal gas law becomes that bridge for us that allows us to equate what we know about a gas and what we know about stoichiometry. Now, if that's a little bit hard for you to kind of put your head around, maybe this picture will help. So again, if you remember back to module 4, I presented this mole map as kind of a way of organizing ourselves to do calculations related to stoichiometry. In module 5, we added to it by talking about the volume of solutions and relating it to moles using molarity. All that we've done now is we've added gases to that mixture, to that scheme, where we can use the ideal gas law to equate the volume of a gas in liters to the moles of a gas in moles. And once we have it in moles, then stoichiometry takes over just the way it has all semester. Now, the best way of going about doing these kinds of manipulations, we got to do some practice problems. So let's take a look at this one. I've got the decomposition of calcium carbonate here. Calcium carbonate in the solid phase decomposes into calcium oxide in the solid phase and carbon dioxide in the gas phase. I've got 41.99 grams of this calcium carbonate. First question, what is the volume of carbon dioxide if the reaction is done at STP? Second, what is the volume of the carbon dioxide if we do the reaction at these non-STP conditions? Why do I have these separated? Well, if we're at STP, we can cheat a little bit. The reason we can cheat a little bit is Avogadro's law. Avogadro's law established for us the molar volume of gas at STP. 1 mole of any gas at STP, so carbon dioxide included, is going to take up 22.7 liters. Again, that's using the IUPAC definition of STP as opposed to 22.4, which is the atmosphere's related one. So if I'm at STP, the process is actually pretty easy. I don't actually need to use the ideal gas law because I can use this relationship to bridge between moles and liters using this Avogadro relationship. So my calculation here resembles just normal stoichiometry. I'm going to turn the grams of calcium carbonate into moles. So I need a molar mass. Calcium is 40.08. Carbon is 12.01. Oxygen is 16, and there are 3 of them. 100.09 grams in every mole. Now that I have my moles of calcium carbonate, I'm going to convert those moles into moles of carbon dioxide. Balanced chemical equation tells me that this is a 1-to-1 ratio. And then finally, I can use Avogadro's law. 1 mole of carbon dioxide is 22.7 liters of carbon dioxide. So calculations wise, 41.99 times 22.7 divided by 100.09. 3 significant figures because my Avogadro's law gives me just 3. I've got 9.52 liters of carbon dioxide. So if I'm at STP, this is all I need to do. That's all I need to do. Just integrate Avogadro's law as the last step. Or if I'm starting with a gas, integrate Avogadro's law as the first step, the first conversion to get me from liters to moles. And then I just do stoichiometry like I've done stoichiometry all semester long. But what if I'm not at STP? Well, if I'm not at STP, then I've got to do something a little bit different. So if I'm not at STP, I need to use the ideal gas law. Now, the first 3 steps of this are going to be, or excuse me, the first 2 steps are going to be the same. Because ultimately, I need to turn this grams of calcium carbonate into moles of carbon dioxide. So I'm going to do the exact same first step. I'm going to do the exact same second step. But here's where things go different. 41.99 divided by 100.09 gives me 4 significant figures, 0.4195 moles of carbon dioxide. So now I have moles and pressure and temperature. I've got 3 of the 4 things that I can measure about a gas. How do I find the 4th? The ideal gas law. So I got to do a little bit of manipulation here. 20 degrees Celsius. I've got to turn it into Kelvin. So 293 Kelvin is going to be my temperature. So PV is equal to nRT. So pressure is 0.973 atmospheres. Volume is unknown. I've got 0.4195 moles. And multiply that by 0.0821 liter atmospheres over mole Kelvin. Ran out of space here. So I'm going to multiply that by the 293 Kelvin also. To get the volume by itself, I'm going to need to divide each side by the 0.973 atmospheres. So volume is going to be equal to 0.4195 moles times 0.0821 liter atmospheres over moles Kelvin times 293 Kelvin divided by the 0.973 atmospheres. So if I do all of that calculating, 0.4195 times 0.0821 times 293 divided by 0.973, the three significant figures, I would get 10.4 liters of carbon dioxide. So if I'm at non-STP conditions, I just need to use the ideal gas law to do that bridge between volume and moles. And so I can go in this direction here, moles to volume. I could also go in the other direction, volume to moles, doing a similar kind of thing, just making the algebra go the other direction. I do have one other practice problem here. I would invite you to try that out on your own. The answer is in the annotated PowerPoint that is in Blackboard. So if you're curious about how to go about doing that, the key to this, these three dimensions, centimeter times centimeter times centimeter, if I multiply them together, I get cubic centimeters. Cubic centimeters are the same thing as milliliters. So that's how you figure out the volume of the bag. But if you want to try that out on your own, compare the answer to what's in that annotated PowerPoint on Blackboard. That'd be some good practice. You're going to get plenty of practice in that review activity as well. But that's all for today, and that's actually all for this semester. So on Friday, module quiz, and that's where we will stop. So have a good afternoon.